This video is for problem number 8 from the homework for discrete probability distributions, and it involves what is known as a binomial probability distribution. With a binomial probability distribution, your answers are either right or they're wrong, correct or incorrect. So we say that there is either a success or a failure. The formula that we're going to be using for this problem is P sub r, which means the probability of event R occurring, is equal to C sub n, the combinations of n items, the P to the R times Q to the n minus R. And C sub n is equal to n factorial, this is the combinations formula, over R factorial times n minus R factorial. This is the combinations of n items taken R at a time. So in this, n is equal to the number of trials, R is equal to the number of successes, n minus R would be then equal to the number of failures. P is the probability of success, and Q is the probability of failure. And so from this problem, we need to determine what all of these things are. So when taking an 11 question multiple choice test, that gives us our n. N is equal to 11, where each question has 5 possible answers. If there's 5 possible answers, then the probability of picking a successful answer on any one trial is 1 out of 5, or 0.2. Therefore, the probability of failure is 0.8 because these two numbers need to add up to 1. Now, in this particular problem, we're not solving for P sub r. We're not solving for P sub r. What we're solving for is R. We want to find R. So there's 2 ways that we could go about this. We could really get into some algebra and rearrange this entire equation or this formula to solve it for R, but that would be very painful. Another way is to use Desmos, and this is the way that I like to do it. So let's put this formula into Desmos, which of course I have already done. And here we are in Desmos. And so I put the formula up here, n factorial over r factorial times n minus r factorial times p to the r, q to the n minus r. When you're entering this, be very careful to make sure that you enter the formula correctly. Okay. Now, we have sliders for n, r, p, and q. Now, if we were solving for n, or for p, we would simply put in the value of n, the value of r, the value of p, and the value of q. But we're actually solving for r. Now, what we want to do is we know that n was equal to 11. We know that p, the probability of success, was 0.2. The probability of failure was 0.8. And we don't know what r is. But what we want is we want an r value that is going to keep p from being less or being greater than 0.05. To answer this question, we need to understand that, let's see, go back to this, it says it would be unusual to get how many or more questions correct by guessing. Well, if the probability is less than 0.05, that would be unusual. So we want to find an R value that's going to keep the answer to this, the probability, greater than 0.05. So if we go back to this, we can use the slider and see how the probability up here changes as R changes. So way up here, let's see. Let's just let R be equal to 0.5, 0.2, and you can see that the probability is getting higher and higher and higher, and then it starts getting lower again, And now we're getting to 0.1, 0.09. We're really, really close to 0.05. 0.416, 0.4124, 0.435, 0.45. We want to stay above 0.05. So at 4.7, we're at 0.055. And so I'm going to stop there because we can't have a fraction of a guess. So we have to round this to the nearest integer. So since r is 4.7 here, and we're almost at 0.05, then we just have to round it up to the next integer of r, so that's going to be 5. So the answer to this question then is simply going to be 5. That would be 5 or more questions. It would be unusual to guess 5 or more questions correct just by guessing and not having any knowledge whatsoever. Of course, it would be unusual to guess 6 or 7 or 8 or 9 questions correct as well, or 10 or 11. And as it says here, we want the smallest possible number of questions. And so the smallest possible would be 5. So once again, we're using the binomial probability distribution formula and just plugging it into Desmos and changing r until we get a p that is 0.05 or close to it. And so we want an r value that's going to be greater than this r value here. Okay, that is question number 8. Question number 9 also involves the probability distribution formula for the second part. And for the first part, it says use the multiplication rule to find the probability that the first 4 guesses are wrong and the 5th is correct. So order is very important in this problem. So we have a multiple choice that has 5 possible answers. So since there's 5 possible answers, let's see, multiple choice questions, each have 5 possible, which I assume. I believe there are 5, if I remember, there are 5 questions. There are 5 questions. I think I left that part off. So that means that n is equal to 5. And so each question has 5 possible answers. So that means P, once again, is the probability of guessing is 1 out of 5 or 0.2. And so the probability of guessing incorrectly would be 0.8. P and Q always have to add up to 1. P plus Q have to be equal to 1. Now we don't need to use that formula for this one. All we need to do is say, well, the probability of a W and another W, another W, another W, and then a correct one. Well, what is the probability of W? W is incorrect. So that was 0.8. So we have 0.8 is the probability of the first guess being incorrect. 0.8 is the probability of the second one, the third one, the fourth one. But now we want to guess correctly on the very last one, so that's going to be 0.2. We could simplify this to 0.8 to the 4th power times 0.2. And I'm just going to throw that in Desmos as well. So I'm just going to go down here in Desmos and put in I believe it was 0.8 raised to the 4th power, and then times 0.2. The answer is 0.08192. And that, of course, is the correct answer, rounded slightly. So 8.19% or 8.2%. So this order is important. We want to have an incorrect, 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 correct. The second part just says, what is the probability of getting exactly 1 correct answer when 5 guesses are made? But it doesn't say that the correct answer should be the first guess or the second guess, the third, fourth, or the 5th. So this is when we're going to use that binomial formula again. So once again, the formula is P sub r is equal to C sub n times P sub r Q to the n minus r. And C sub n is n factorial over r factorial times n minus r factorial. And I'm going to do this in Desmos again. In this particular case, n was equal to 5, and p was equal to 0.2, q was equal to 0.8. The number we want to know, let's see, go back to what was r in this particular case. What is the probability of getting exactly 1 correct? So we want to know, so that means that the number of successful outcomes, r, is going to be equal to 1. And that's everything that we need. We have n, we have r, we have p, and we have q. Those are the 4 things that you need: n, r, p, and q. So let's plug those into our formula in Desmos. And so n was 5, r is 1, p is 0.2, and q is 0.8. And so it's telling me that the probability is 0.4096, which I believe was the correct answer, 0.4096. Now you could of course do this by hand, but I'd suggest that you use Desmos. Desmos makes the actual computations much simpler. You do need to know the formula. You do have to be able to put the formula into Desmos, and that's not difficult to do, and then use the sliders. All right, that was question number 8 and question number 11. Both involved, to some extent, the binomial distribution or binomial probability formula. All right, hope the video was helpful.